Yeah, welcome back after the break. So, what we are talking about the common emitter amplifier, and what we are looking for is that Zm transimpedance of the amplifier we like to stabilize, and it should be defined by the feedback network element. So, as this table suggests that if we are looking for this Zm to be stabilized by the negative feedback, then A should be Zm. So, this is the configuration we have to use, where we need to sample the signal in the voltage form, and we have to mix the signal at the input in the shunt configuration, or we can see that the current form, or we can say it is shunt configuration. And so, that based on this table and the requirement, the feedback configuration, it is voltage shunt or shunt feedback configuration. And this is the corresponding model of the configuration, where this is the amplifier, forward amplifier, and this is the feedback network, and here we do have the sampling of the output voltage, and here we do have the mixing of the primary input and the feedback current to get the input current for the amplifier. So, we can say that in this circuit input signal it is current, and the output signal it is voltage. So, the forward amplifier, it is its gain, it is Zm. So, its unit, it is ohm, and then the unit of the feedback network's transfer function beta f b, it is mho, and the input. Now, next thing is that we need to find what is the corresponding input resistance and output resistance of the actual circuit. Namely, if I consider this circuit, what is the corresponding input resistance and the output resistance of the circuit. So, in the next slide, what we can do, first of all, we have to sample this voltage, and then we have to make a connection here. Probably we can make a bridging element from output to input, and this unit supposed to sense this voltage here at the output, and it is supposed to produce the current at the input port. So, in the next slide we are going to have the corresponding circuit, and yeah. So, here we do have the common emitter amplifier along with its feedback arrangement, and we are also adding one capacitor, so that the DC operating point of the common emitter amplifier, it is not getting disturbed by presence of this RF. So, this RF, it is sensing a voltage here, and it is providing a current here. So, if you consider the idealistic situation, then if I say that if this point, if it is connected to say ground, the current flow here, it is V o, if I call this is V o divided by RF. So, that is the feedback current. So, I equals to V o divided by RF. So, from that you can see that this I f equals to V o divided by R f. So, from that we can say that beta f b equals to 1 by R f. So, if there is no load at this output port of the feedback network, namely if I connect 0 resistance to ground, then whatever the current we are getting, that is the I f, and that gives us the, and using this equation we are getting the beta f b, which is unloaded. So, we can say beta f b of this feedback network, it is 1 by R f. In this circuit, of course, primary input it is I s. Note that this resistance here, bias resistance R b, it is quite high compared to the other circuit. So, we may ignore this resistance for our linearized analysis or AC analysis, and then of course, we have to consider this is AC ground, and the output node here, which is the collector terminal. So, this is the collector node, and then we do have the emitter node here. So, that is this node is the emitter node. So, let me use this point here, which is of course connected to ground. So, this is of course, it is connected to the actual ground. On the other hand, at the base, this base terminal, it is the input terminal. So, this is the base terminal, and the negative side of the input port, it is connected to the ground. So, this is the corresponding emitter terminal or the negative side of the input port or negative terminal of the input port, and this emitter, it is connected to again ground, and the resistor R f, it is connected between R c and not R c, the collector and the base through this capacitor, and for signal we can assume that this capacitor, it is working as a short. So, we can see that this R f, it is bridging this collector terminal and the base terminal for the signal. So, that is how this R f, it is shown here in this equivalent circuit. Now, base to emitter, we do have R pi, and then collector to emitter, what we have, it is we do have internal voltage, internal signal voltage, which is beta times R naught into I in. In fact, this voltage we need to write in terms of the input signal, which is current, because our main focus is to define A of this circuit, rather Z m. So, originally or most of the time what we use the internal circuit, it is not an equivalent circuit, where we do have the internal current source, which is beta times I b or I in parallel with R o, which is the conductance here. Now, this I b, it is same as I in. So, probably you can write this is I in, and this circuit, not an equivalent circuit, we are writing here in this form, which is Thevenin equivalent. So, in summary, we can say that the internally developed voltage here, it is beta into R naught into I in. Of course, this polarity of this current, positive current, is from collector to emitter. So, that is why we do have minus sign here and plus sign here, and this R naught, it is directly providing the Thevenin equivalent resistance. So, in summary, this is the small signal equivalent circuit of the amplifier, considering RF into the picture, and of course, ignoring the base bias resistance, and at the input we do have the we are expecting the signal should be current. So, this is the corresponding input stimulus, ideal stimulus I s. So, in the feedback circuit the primary input is it is this I s, and on the other hand output it is the voltage here V o. So, we can say that V o is the corresponding voltage. Also we can see that this R C it is connected between collector and VDD, and VDD it is AC ground. So, this R C you can connect from collector to the AC ground, which is also for AC model you can, or AC or small signal equivalent circuit, you can say that this is also connected to ground. So, that is how we can see that the transistor level circuit it is getting translated into the desired model, and the model it is it consists of the different elements, the feedback network as well as the main amplifier. So, let me clear up the diagram here again. So, what we have here it is output to input, this RF it is working as feedback network. So, we can say that beta FB it is 1 by RF. Input resistance of the circuit it is R pi, and output resistance in this case it is R o, which is also getting loaded with R c, and typically this R c it is much smaller than R o. So, it is better to internalize this R c with this amplifier. So, once you modify this circuit, or rather once you take this load within this, then the internal voltage it need to be changed in this form, where you can see that the voltage available here it is once we have the R c, the corresponding voltage V o it is equal to internal voltage beta into R o into I in multiplied by R c divided by R o plus R c, or you can say that beta into R o in parallel with R c multiplied by I in. So, this whole circuit it can be said that it can be represented by Thevenin equivalent voltage source, where the voltage it is Thevenin equivalent voltage is given here, and the Thevenin equivalent resistance of course R t h is R o in parallel with R c. So, the whole circuit it is getting reflected here in this form. So, the R c it has been consumed, now the circuit it is unloaded. So, with this modification you may say that this R out instead of R o it is R o in parallel with R c, and in this model the corresponding A which is of course this is Z m. In this model it was beta into R o, but once we take this R c within the circuit, then the corresponding Z m, or we can say that Z m dashed, which is load affected Z m, it is equal to beta into R o in parallel with R c. So, that is the A, the forward amplifier gain considering the load. The other things of course, it is as I said that the output resistance got changed. So, either you may say this is R out dashed, which is R o in parallel with R C, and this can be well approximated by R C for all practical purposes. Likewise, this also can be well approximated by beta into R C. And then if you look into the feedback network, and if you try to see what is the corresponding input resistance here of the feedback network, what we say it is R in beta. If I consider the other side, it is not loaded, that means it is shunted to ground, then it is equal to R f. Likewise, if I consider the output port, and if I say that the output resistance of the feedback network R out beta, that is which is driven by a good voltage source. So, if I consider it is a good voltage source, then it is in ideal condition, this is also R f. So, along with the input resistance of the forward amplifier and output resistance of the forward amplifier, we also have input resistance of the feedback network, which is equal to R f. In fact, R out beta, it is also R f. So, with this set of information, we are now in a position to make use of the equation, particularly what will be the feedback system trans impedance ZMF. But then we have to consider that once you have this beta R in beta connected here, we should consider its loading effect on the circuit, it is negligible. So, likewise the loading effect of this input resistance here on the feedback network should also be considered as negligible. So, that gives us an idea that what may be the meaningful range of this R f, or what may be the meaningful range of this beta f b. That is very vital to construct a practical feedback circuit, where we can directly use the equation to find what is the what are the changes are happening, namely what is the value of the ZMF and what is the value of R in and R out. Okay. So, in the next slide we are going to do that. So far what I said is Zm it was beta into Ro, but more important thing is that Zm dash rather, it is equal to approximately equal to beta into Rc, and R out dash it is Rc, R in it is R pi, beta Fb it is 1 by Rf, and then next thing, as I said, that we need to find what is the suitable range of this Rf. And to get that, since we are sensing the signal here, the voltage, one condition it is that R in beta it should be much higher than R out here or R out dash. Likewise, to avoid the loading effect here or to ignore the loading effect here, the R out of the beta network it is it should be much higher than R in, and as I said this is equal to R f, this is also equal to R f, and R in it is R pi, and R out dashed it is R c, which gives us that R f should be higher than, much higher than R pi and this also R c. And whenever we say it is much higher than this, all practical purposes what we can do, we can say that R f it is higher than or equal to 10 times of r pi or 10 times of and 10 times of r c. So, so that gives us the lower limit of R f. On the other hand, if I consider the other condition, namely a dash into beta f b should be much higher than 1, and a dash it is beta into R c. So, we can say that beta into R c and beta f b on the other hand it is 1 by R f. We want this should be much higher than 1, or we can say that R f it is much lower than beta into R c. So, if I combine say this lower limit and upper limit of R f to really make this feedback system effective, we can get a suitable range of R f. And once you get that, and once you make sure that both these conditions we are satisfying, then we can say ZMF equals to Zm dash divided by 1 plus beta f b into Zm dash, and that can be well approximated by ignoring this 1 with respect to this. So, we can say this is approximately 1 by beta f b, which is equal to 1 by R f. So, it is giving us R f. So, ZMF it becomes equal to R f. So, we can say that in this circuit Zm of the feedback system, once we have this R f, it is equals to R f, which means that ZMF equals to all practical purposes equal to R f. And the input resistance on the other hand, as you can anticipate that input resistance it is getting reduced because of this shunt connection. So, we can see this is equal to R pi original R in getting reduced by 1 plus beta f b into Zm dash. In fact, this is also coming in parallel with R f, but if you see this part first. So, this is R pi divided by, if I say that this part it is dominating over 1. So, we do have beta f b it is 1 by f, 1 by R f, and then we do have beta into R c. So, that is equal to so R pi here, and within the beta we do have Gm and R pi. So, that R pi you can cancel. So, this is coming R f divided by Gm into R c. So, the initial resistance here it was R pi, now that is becoming R f divided by Gm into R c. On the other hand, if I consider the output resistance, so let me use this space here and use different color. So, this resistance it is output resistance it is R c, and that divided by, so that is the R out dash divided by again 1 plus beta FB into Zm dashed, and its expression it is beta into RC divided by RF. So, this is it can be well approximated by RF divided by beta. So, both R in and R out, they are getting reduced by the same factor, and so in this circuit we can see that output resistance, it is even after considering this R C within the circuit, it is RF divided by beta, and input resistance here it is RF divided by Gm into RC. Of course, we have ignored this resistance and that should not be a problem, because the typical value here it is much smaller than this RB. In fact, RB it is much higher than R pi itself, and this feedback resistance it is a reduced version of this input resistance. So, naturally it should not be having any problem. So, now next thing is that let us also look into the consequences on the other parameter. So, here what we said is Zm it is getting defined, it is defined by the this Zm, rather Zm it is changing from beta into RC to this RF, and we like to see what other changes are also happening on the other parameter, namely voltage gain and then current gain and then transconductance. Okay. So, in the next slide again we will be using the overall consolidated table to check what are the changes are happening there in other parameter. Yes. So, this negative the feedback system here it is of course, we are expecting that there will be changes on the other parameter, but if you see the configuration here, we do have this configuration where the main parameter it is Zm, and so we already have seen what kind of changes are happening in Zm, and we like to see what are the changes are happening in the other parameter, and to get the information we need to see this column. So, as I said that this circuit it is having the input not input the current gain AI. AI, if I consider this equation, it is giving us an expression AI equals to Zm divided by R out. So, since this AI it is having an expression of Zm divided by R out, whether they are load affected or not, both of them are getting reduced, this as well as this, by the same desensitization factor, and hence no changes. So, likewise, if I consider the voltage gain, which can be its expression can be obtained from this entity, namely voltage gain it is Zm divided by R in. So, this is equal to Zm divided by R in, and both Zm and R in are dropping by the same factor, and hence no changes. On the other hand, if you see the transconductance Gm, and if you look into this entity, so that gives us Gm equals to Zm divided by R in and R out. Both R in and R out getting reduced by the same factor. Zm is also getting reduced by the same factor. So, we are expecting that this whole entity, it is getting increased by desensitization factor D, which means that Gmf, it is getting increased. This is getting increased by 1 plus beta Fb multiplied by Zm dashed. And for this circuit, this Gm, it is Gm of the transistor, and this entity we already have discussed. So, that is, we can say it is much higher than 1, and its expression, it is beta into R c, and beta F b, it is 1 by R f. So, that gives us Gmf equals to so this is the quantity. It is saying that Gm, it is getting increased by this factor with respect to its original value of Gm. Now, let us look into a numerical example associated with this application circuit to get a feel of the value of different parameters, or particularly how to get the value of this Rf. So, in the next slide we do have the same example having specific value of different bias elements as well as the device parameters. So, in this circuit, the value of this R c, it is given here, it is 5 k, R b, it is 940 k kilo ohm, and supply voltage, it is 10 volt, and let you consider V b on, it is approximately 0.6. Early voltage of the device, it is, let us assume it is 100, beta of the transistor, current gain, it is 100. Now, with this information, quickly we can say that the DC current here, it is 10 microampere, and the beta is 100. So, we can say that the collector current, it is 1 milliampere, and so that gives us the R pi and Gm and so and so. So, we can see that R pi, the input resistance R pi here, it is 100 beta divided by the Gm, and the Gm, it is 1 milliampere divided by Vt 26 millivolt. So, that is equal to 1 by 26 mho. So, R pi, it is equal to 2.6 k. So, that is the input resistance of the main circuit. The output resistance, if I consider load affected, so that is in fact, with this value of early voltage, we can say that R O intrinsic output resistance, it is 100 k, 100 volt divided by 1 milliampere. So, this is equal to 100 k, and R out dashed, it is R out dash it is equal to R O in parallel with R C, and R C it is 5 k. So, we can say that 5 k it is dominating. So, we do have the input resistance, we do have the output resistance, and also the Zm or rather let you consider directly Zm dash. Zm dash it is beta into R C. So, that is equal to beta is 100, R C it is 5. So, that is 500 k. Now, using this information, let us try to see what is the suitable range of this beta FB or suitable range of RF. So, first thing is that RF, which is also equals to R in beta and R out beta. And by considering the situation such that the loading effect of the R in beta on the amplifier, if we have to ignore, then we can say that the R in beta it should be much higher than output resistance R out dash. So, that is equal to R out dash. So, that is equal to R C, and this is of course R F. On the other hand, the other condition it is we want R out beta is much higher than input resistance R pi. So, combining these two we can say that, and this is also R F. So, R F should be higher than, much higher than R pi, which is 2.6 k, and also it should be higher than, much higher than this R out dashed, which is 5 k. Now, if I say that these two are, in fact, this is defining the lower limit. On the other hand, if I consider beta FB into Zm, which is giving us 500 k. So, 500 kilo ohm divided by Rf should be much higher than 1. So, this is giving us that Rf should be much smaller than 500 kilo ohm. So, by combining these two limits, the upper limit and the lower limit. So, we do have the upper limit and the lower limit. We can say that RF it is having a meaningful range, and its lower limit it is 5 k, upper limit it is 500 k. And let you consider one example. So, we can consider say Rf equals to say 50, which is definitely helping us to satisfy both upper and lower limit. And if I consider Rf is equal to 50, then beta into beta Fb into Zm dash, it is we do have Zm dash, it is 500, and beta F B is 1 by 50. So, this is equal to 50. So, this is equal to 10. We can say that this is much higher than 1. So, we are satisfying this condition, and then we can say that desensitization factor, actually it is to be more precise, it is 11, or rather we can say that this is 10. So, we can say that ZMF, it is Zm dashed divided by this desensitization factor, or approximately you can say this is divided by 10, and this is equal to 50 K, which is same as the value of this RF. And the input resistance on the other hand, it is of the feedback system, which is 2.6 K divided by D. So, either you can consider D is equal to 11 or approximately equal to 10. So, we can say if I consider it is approximately 10, so it becomes 0.26 K, or you may say 260 ohms. The output resistance on the other hand, it is R out dashed divided by D. R out dashed, it is 5 K divided by either you consider 11 or approximately 10. So, that gives us a value of 500 ohms. So, in summary, what we can say that if we put this resistance, this is equal to 50. So, that gives us the output resistance here, which is 500 ohms. Input resistance to this circuit, it is 260 ohms. Of course, these are approximation, in fact, they are even lower than that, which means that the input and output resistance, it is getting decreased by the shunt configuration, and Zm, we said it is getting decreased, and the Zm part, it is equals to 50 kilo ohms. Now, you can find what will be its effect on AV and voltage gain and current gain by considering that consolidated table, and also in Zm. In fact, so we already have discussed that this will not be having any change, this will be having a change, and that gets increased by a factor of D, which is approximately 10. So, this Gm, it will get increased by 10, and then voltage gain and current gain approximately remaining unchanged. So, that is about the numerical examples to say that by connecting this feedback circuit, what kind of changes we do have. So, likewise we can go for other examples. So, here we do have another circuit which is again common emitter amplifier, but here the objective is it is different, namely we want stable Gm, and in case if you are looking for stable Gm, then the corresponding configuration here, as this table suggests, that it should be current sensing and series mixing, or you can say series configuration. So, we will be discussing this one in the probably in the next lecture. So, let me break here, and then we will continue this topic of discussion. Thank you.